Our goal is to obtain perfect reconstruction. Perfect reconstruction is defined as a reconstructed signal which is identical to the original signal except for a delay. So here we have our reconstructed signal and we have the original signal with a delay, in this case ND is this delay at the original sampling rate. This delay usually results from our filtering and the downsampling and upsampling operations. So to obtain perfect reconstruction, we can simply take a look at the output of our synthesis filter bank. The structure of the polyphase analysis and synthesis filter bank can be seen also in the following picture. So here we have our original input signal. We have here this delay z to the power of -1. We have downsampling, we have a transfer function or filtering, and then we will have the output, and then it goes to the synthesis filter. Then we have upsampling with delays, and we have our reconstructed signal. So the structure of the delays and downsamplers on the left of the analysis polyphase matrix, it's converting a sequence of samples at high sampling rate into a sequence of blocks at the low sampling rate. It's called blocking. And this is what our Python function x2polyphase is doing. Conversely, the structure to the right of the synthesis polyphase matrix converts a sequence of blocks at the low sampling rate into a sequence of samples at the high sampling rate. It's called deblocking, and this is what our function polyphase2x is doing. And here we can see that we will obtain perfect reconstruction if we have the synthesis polyphase matrix as the inverse of the analysis polyphase times a delay by d blocks. So here we have the inverse of the analysis polyphase, and we have a delay of d blocks, where d here is the delay at the downsampled rate. This is basically again like in our block transform case, and this is now the constraint for obtaining perfect reconstruction. The question is, how do we obtain filters for perfect reconstruction? How do we invert a polyphase matrix containing the polynomials? And how do we get good synthesis filters? A simple approach is analog to the orthogonal block transform matrices, where the inverse is simply the transpose matrix. There, the analysis and synthesis filters are identical, except for the time reversal for the analysis filters. The corresponding property of polyphase matrices is called Peri-Unitary, and you can see more in this reference here, multirate systems and filter banks, and it's defined by this equation here. So the transposition is the case for real valued coefficients in the polyphase matrix. Otherwise, we need conjugate transposition for the coefficients. This definition is very similar to the definition of orthonormal matrices, except that we have the z to the power of -1 on the right hand side, and that corresponds to a time reversal. The advantage, or rather one of its advantages of a polyphase matrix with this property is that we don't need to explicitly compute its inverse. We just need to transpose it and replace all z's by z to the power of -1. Observe, if our polynomials in the polyphase matrix only have zeroth order, only constant, no z, only z to the power of 0, which is equal to 1, then the polyphase matrix is identical to the transform matrix, for instance, in the case of our DCT4. And we obtain the simple case if our filters are no longer than n and they fit into one block.